Hello, and welcome to sections 17.2 through 17.3, as well as 17.5. In these sections, we're going to be looking at the general plane motion of a rigid body. So what we want to be able to do is analyze planar motion of a rigid body using equations of motion. So if you remember previously for particles, our equations of motion were just sum of forces equals mass times acceleration. Now that we have a rigid body, we also have to account for rotation. So there's a series of equations that we can use. So what I'm going to do is I will be writing those out over here. So let's start with translation. So there's two types of translation that we care about. So I guess general plane motion is a combination of translation and rotation. So a body can just translate, so it could go left or right, up or down, or it could move at some angle. But as long as it's moving in a straight path, so if you kind of focus here on the center of gravity, the orange speck, as long as that center of gravity follows a straight line, that's just rectilinear translation. And those kind of problems, we will want to use the XY coordinate system. So we could rotate it, say, for the case where it goes at an angle. So that's going to be sum of forces in the x direction. I'll assume that's to the right, equal to mass acceleration of the center of gravity in the x direction, and then sum of forces in the y equal to mass acceleration of the center of gravity in the y direction. So these carry from what we saw with our particles. The other type of motion that the other type of translation, it would be curvilinear. And so if it's curvilinear translation, what that means is if we, again, focus on the center of gravity, so that means that it's going to be moving in some kind of an arc or a path. It could be some kind of an S-curve. It's basically, if we plotted the location of G, the center of gravity, over time, we would see that it doesn't form a straight line. So in that case, we want to use something like normal tangential or r theta coordinates. So the book is going to generally just use normal tangential. So we'll have sum of forces in the normal direction equal to mass acceleration of gravity in the normal direction, but this doesn't tend to be very useful. So instead, what we do is we saw this in the last section, we rewrite this as mass times omega squared times the radius to the center of gravity. And then sum of forces in the tangential direction. So again, I'm just putting arrows on here. You'd have to actually determine manually where these arrows go. So that would be mass acceleration of gravity tangential. And we would rewrite that one as mass alpha RG. And we covered the derivation of those in the last section. Now we can also use r theta coordinates. The book generally doesn't. So again, this is just anything where we have some curved path. It can just focus on the center of gravity. So that would mean it not moving in a straight line. So we could also use sum of forces in the r direction. And again, I'll just throw some arrows on here just for practice, but you'd have to determine which way the radial direction is. And so simple form is mass acceleration of gravity in the radial direction, but that again is not very useful, so we generally expand this out, and we expand that using our particle kinematics, so the stuff we learned back then. So it's the same stuff. So that's going to be RG double dot minus RG omega squared. And again, if you remember, the acceleration in the radial direction is just r double dot minus r omega squared. So that's where that comes from. And then we also have sum of forces in the theta direction. And again, I'm just going to put a direction arrow on here. Mass, acceleration, center of gravity, and theta. So we're always looking at the center of gravity when we track translation. So this will become mass, and then we would just expand our a theta term here. and A theta will become RG alpha, and plus 2 R dot, so RG dot times omega. So you could have derived these on your own. So that is for translation. So most of the time, you basically ask yourself, is the center of gravity going to be translating in a straight line? If so, try to use the XY coordinate system. If it's going to be translating in a curved motion, try to use the NT. If you really have to, R theta is an option, but most of the time you don't need to use it. So that is for translation, but general plane motion also has rotation. And so we get sum of moments equal to generally some I alpha, and then there could be some other terms here depending on what we're doing. So let's look at those. So there are 3 of those. So these are the case where the body is rotating. So again, it could be rotating about g, it could be rotating about some fixed point, or just it could be rotating arbitrarily. So if it's any point, so if we just have any random point in space, we get the sum of moments about any point P. I'll assume right hand positive. So again, this is all planar, so we are ignoring the z-axis. So all of these moments will be about that z-axis at some point. So we'll include IG alpha. So our vector moments, are kinetic moments. So kinetic moments are caused by the accelerations. So kind of if we take a short little detour here, so a traditional moment, you might remember, is moment equals force times distance. But also, we know that F is equal to ma, lowercase m. So if we sub in this ma for this F, we get what's called a kinetic moment. So in this case, our moment, and we use a different term for that. It looks like, so it's kind of like that. That's a kinetic moment. So our kinetic moment is then mass, acceleration, and distance. So sum of moments about any point P, IG alpha. Sorry about the screen freezing there. There we go. Plus the R vector, 2G from P, if you want that vector. And we're going to cross that with our mass accelerations. So generally we want to scalarize this for right now. So we can write this as a scalar this way. Sum of moments about any point P, IG alpha, plus, so I'm going to use XY coordinates, but you can do the same thing with the other coordinate systems if you run into them. So mass times the acceleration of gravity in the x direction times delta y. So how far away is it between this point P and the center of gravity in the y direction? And then plus mass acceleration of center of gravity in the y direction, delta x. Let me make sure that's separated. So that's one of our equations. So when we do this about point P, we get this long form. Most of the time we want to do it at a special location. So if we do it at the center of gravity, so if we take the sum of moments about the center of gravity, then what will happen is this delta y and this delta x will go away, because the distance between our point and our center of gravity is 0 in both cases. So we'll end up with just IG alpha. And then the final case is if I do it about a fixed point or an instantaneous center. So that would be sum of moments about some point O, or you can do some, or you could say sum of moments about an instantaneous center. It's the same thing in this case. That is going to be IO times alpha. Alright, so to explain this, I've drawn this diagram down here. So basically, if I have some fixed point O, this can't move. When I have G, and say G is rotating about point O, or the instantaneous center. So I'll have a tangential direction, and I'll have a normal direction, and there'll be some radius between them, or some distance. So normally I would write, I could treat this as a point P for right now, and say it's IG alpha plus mass acceleration in the tangential times the radius. The acceleration in the normal will go through the fixed point here, so it won't produce anything, so that point will go away. So I end up with basically this equation here. And then what will happen, so this would be our sum of moments about O, generically. And then what will happen is I sub in for AG, so the acceleration of gravity in the tangential direction, so I do the same thing that I did up here, where it'll become alpha times R. So we end up with IG times alpha plus mass quantity alpha times R. And then we get the R equal to the sum of the moments about point O. And then if I clean this up, what we get is I have a common alpha, and I get IG plus mass, and I have radius times radius, which is radius squared. And that's all equal to sum of moments about naught. And so what you should see here is IG plus mass radius squared. This is parallel axis theorem, and that is how we get up here to I naught. So the alpha stays, and so that's where the I naught comes from. Alright, so in the next video we will actually apply these equations to a problem undergoing translation only.